Welcome everybody. On this blackboard you'll find all the basic facts that you'll ever need for high school optics, or even maybe for undergraduate wave optics when you're beginning your studies in physics. This is a very condensed summary. There are a lot of videos on this channel explaining all the details and giving examples, but they're in German, I'm afraid. So we start for what I call the standard text for every diffraction or interference problem, which explains in general why there is an interference pattern whenever coherent light hits a diffraction object, for example a double slit, as in this picture. So what you see here are the wave fronts of the electromagnetic light waves that approach the diffraction object. So throughout wave optics, we use the model that light can be described as an electromagnetic wave. Here depicted is the enveloping curve of all the electric field vectors that oscillate very rapidly in a light wave. Omitted here is the magnetic field vector, which stands perpendicular. And here you see the wave fronts, meaning, for example, that all the electric vectors look like this. This here are the wave fronts. And very important is that the light that we use is coherent, meaning that different waves have the same phase relation, meaning that the electric field vectors always have a constant angle and that the angle is not changing. I'm not going into any more detail here. Coherence is a pretty deep subject. Usually we use a laser which fulfills this condition automatically. Laser light is always coherent. So then what happens? The light waves that arrive here at the slits of my diffraction object get diffracted. Meaning here behind each slit there are so-called elementary waves. The wave fronts here are semicircles. We apply here Huygens principle, well known from mechanics, for mechanical waves. Here in optics it doesn't make much sense physically, but it leads to the right results. That's why in school we always use Huygens principle. So whenever these elementary waves overlap, interference happens. And this is what leads to the characteristic pattern that you see on a screen. Here in the middle, where no light at all should be, because here light can't come through, you see a bright spot of light. Then there's darkness, then again bright spot, then darkness, then bright spot, darkness, bright spot, and so on. The same in the other direction. And this is what is called an interference pattern. The explanation is as follows. Two elementary waves can overlap in a constructive manner, meaning the electric field vectors of the wave that comes from here and the wave that comes from here point in the same direction. Then they add up and I get a bright spot, called a maximum of intensity. And this is always the case when the optical path difference is a natural multiple of the wavelength of the waves. Here you see one wavelength, lambda. We're going to talk about that shortly. And whenever the interference is constructive, you see bright spots or lines or dots on the screen, depending on your diffraction object. Interference can also be destructive, meaning that the electric field vector of one light waves points that way and the other in the other direction. And then they cancel out. And then there actually is darkness. And it should not be called shadow, because shadow means light would be completely blocked away. This is not the case. Electromagnetic waves arrive here, but they cancel each other out. And this is why we get dark spots or lines on our screen. And now the single most important thing to understand when dealing with interference patterns is the optical path difference. In optics, we're always using the Fraunhofer Approximation, so called after the German physicist. which is always valid or gives very good results whenever here the distance between the slits is much, much smaller than the distance to the screen. And in optics, this is always fulfilled because here we have millimeters or even micrometers, and here we have meters in general. So this here is fulfilled, and then we can say that here the a wave ray is this white line here along which the electric field oscillates. So the wave ray gives the direction of propagation of the light wave. We may assume that these wave rays here are parallel. If you imagine here, there's, for example, 1 micrometer and the screen is 2 meters away. And then if you draw 2 lines from these slits to the screen, they are almost parallel. And that's the Fraunhofer approximation. So we may assume the wave rays are parallel, and then in a very far away point on the screen they do meet after all. But here in the beginning it's okay to say they are parallel. And then if I make this perpendicular line to the second wave ray, then here this little orange bit, that's the optical path difference, because this bit has to be traveled more by wave ray 2 to reach this point on the screen. And here this accounts for constructive or destructive interference, because the length of this piece determines if this here is 1 wavelength or say 1/2 wavelength and so on. And now using this Fraunhofer approximation we get a very simple formula for calculating the path difference. In general you would have to use Pythagorean's theorem and the formulas would be a mess. But here using this approximation it's very easy, because I have a perpendicular triangle here, and alpha sub n is the angle at which I look from the middle here towards, for example, maximum of order n on the screen. This is alpha n. Then this angle occurs here as well, because the sides are each perpendicular, here, here, and here, here. So this is simply the length of the hypotenuse, which is g, the distance between 2 slits, times the sine of this angle. And now with this formula put together with those, we get 2 very important formulas for the double slit, which tell us how to calculate where on the screen occur the maxima of order n and the minima. So a maximum of nth order lies under the angle alpha n, which satisfies this equation. The optical path difference, g times the sine of alpha n, must be a natural multiple of the wavelength of the electromagnetic light wave, or 0 is also allowed, because here in the middle of the screen the path difference, of course, is 0 here. This orange thing becomes 0. So in the middle of the screen, the electric field vectors always meet like that and make constructive interference. So in the middle, there's always a maximum, a bright spot, which is also called the maximum of 0th order. And if I call the angles under which I look at the minima, the dark spots on the screen, beta sub m, then here the path difference must be an odd multiple of lambda over 2. Odd because if I, for example, I take 2 here, then I would have 2 times lambda over 2, which would be lambda, which would lead to a maximum. So here you have to take all the odd numbers, meaning 2m minus 1, m is a natural number, times half of the wavelength. Then the electric field vectors meet like that and cancel out, and there is darkness on the screen. And as I said before, this is just a summary. We're not giving examples on how to compute the distance on the screen or how to find these angles, but a very useful formula here from trigonometry that you have to use if you want to find the distance between the maximum of order 0 and the nth maximum is that here this length dn, d sub n, is a, the distance from double slit to screen, times the tangent of this angle here. And if you put these formulas together, you can solve almost all the questions for the double slit experiment. So now we're taking a closer look at all the different diffraction objects, starting with the single slit. Even if I have only one opening and shoot laser light at it, I get a diffraction pattern, which is very strange because I would expect to simply get a red dot. If I use a red laser pointer and point it at such a single slit, I should get a red point and shadow around it, but what you see actually is exactly such an interference pattern. To explain this, we assume that from every point of the single slit, such elementary waves emanate, Huygens principle, which again makes no sense at all physically, because here inside the slit there is nothing to emit light. But as I said before, it yields the right results mathematically, so we use it. And here are some wave rays of these elementary waves in a certain angle direction. The angle here is called phi. And now I split up all the wave rays in two bundles, here red and blue, such that here this is B is the width of the slit, B over 2, and this is also B over 2. And now if I look at here this first red wave ray and here this first blue wave ray, then their optical path difference is given by this length, B over 2, times the sine of this angle, because here is also the angle phi. And now if this equals lambda over 2, then these two cancel out, because then we have the condition for destructive interference. And if these two have this path difference, then of course these two have this path difference, and so on. So all wave rays or the corresponding electromagnetic waves cancel out. One gets left out, but we ignore that because we have a lot of wave rays. This is a somewhat problematic derivation of this formula, but it works for the first minimum. There are similar arguments for the higher order minima, but I'm not going into any detail here. Long story short, if you look at the intensity at the screen, which is how bright you see the light spots, then you get this curve. And this is important for later. The intensity is proportional to the length of the resulting electric field vector of the electromagnetic wave at that spot. You get a curve like that, very high peak in the middle, which you would expect because there classically most of the light or all of the light should be. Then there's a dark spot, there's really no light at all. And this angle of the first minimum can be calculated using this relation. If I take times 2, then B times sine of this angle must be lambda. And then I have a formula for calculating here the first zero of this intensity curve. The same holds for the second zero. Then I have B times sine phi 2 must be equal to 2 times lambda, and so on. And here are again maxima. There will be bright spots, but here in comparison to the maximum of 0th order, they will be very much less bright. And this is the diffraction pattern of a single slit. Here, to calculate where these maxima lie is more difficult. We are not going to talk about that, but the zeros can be found exactly using this formula here. Now it's also possible to derive a formula which gives you the complete intensity curve function, which you find here. This is I sub 0, the intensity in the middle of the screen, times the sine squared of an argument z divided by z squared, where z contains all the important constants. Of course, we need to have a dependency on the width of the slit, B. Of course, it must depend on the wavelength and of course on the angle under which I'm looking at the screen. And if you plug this in here and plot a curve for given values of b and lambda, then you get exactly the intensity curve for a single slit. There are two interesting special cases. If the width is much bigger than the wavelength, then you get one sharp peak, and then here these maxima are barely visible at all and occur very near to the 0th maximum, which means you will only see one bright spot on your screen. So this is the special case of geometrical optics, where you can assume light goes simply through the slit and there's no diffraction at all. The other very important special case is when the width is smaller or even much smaller than the wavelength of the light, then the intensity curves looks like that. So almost independent of the angle, I get the same intensity, though the whole screen will be illuminated. And this is the special case of an elementary wave, because as you see here, in all directions, electromagnetic waves propagate into space. Everything is contained in this formula when you plug in a value for b that is much smaller than the wavelength. Next, we take a closer look at the double slit, which is the classical diffraction object. Almost everything has already been said, especially these formulas here, so we're going into a little bit more detail. Sometimes you are asked to calculate the maximal number of maxima that can be seen on a screen, assuming the screen is wide enough so that all fit on the screen, or the screen looks like that. So like a semicircle, so all the angles can be seen at the screen. Then you need to realize that the maximal optical path difference you can ever get is when this angle here approaches 90 degrees. Because try to imagine those wave rays get bent up more and more and more and more. And then for alpha exactly 90 degrees, both wave rays would be parallel and the path difference would exactly be g, the distance of the two slits. So the maximal path difference is g, and then of course the condition for a maximum is that the path difference needs to be a natural multiple of the wavelength. So at most this expression here can be g, which gives you the maximal order of a maximum is g divided by lambda, and then you need the floor function because n must be a natural number. And then, because this pattern here is symmetric, if the maximal order, for example, is 5, you're going to see 5 maxima here, 5 maxima down here, and the maximum of order 0, so 11 put together. And so you need to take this number times 2 and add 1, and this is the maximal number of maxima that you can see on a screen. For most double slits, of course, depending on the actual width or distance g, an approximation for small angles holds and gives very good results and simplifies the calculations. If your maximal angle, say, is about 5 degrees, then sine alpha equals tangent alpha is a very good approximation. And then if you put this formula here, sine alpha is n lambda over g, together with this formula, the tangent of alpha is dn, the distance from 0th maximum to the nth maximum, divided by a, you end up with this. And then you get a very simple formula for dn. This is the number you're actually looking for, the distance of the nth maximum to the middle of the screen where the 0th maximum lies. This is simply n times lambda over g times a. And then you see, using this approximation, that the difference of two neighboring maxima is always a constant. Oh, this is still German, so I need to write with a C. This is simply lambda over g times a. So all the maxima here have the same distance. And the same goes for the minima. If I call the distance between the middle of the screen and the minimum of order n en, then I get this formula using the small angle approximation, And then with a little more effort, you can show that here En plus 1 minus En, please do the missing steps yourself, is also lambda over G times A. So all the maxima and minima are of the same distance. Between the neighboring maxima and minima have the same distance whenever this here is a good approximation. And now one of the most important observations. What you see here in white chalk is the intensity curve of the so-called ideal double slit, meaning that actually both slits are very, very, very thin and send out elementary waves. So we are in this case here. Then even towards alpha equals pi over 2 or 90 degrees, the intensity of a maximum should be the same as in the middle. Now when you do the experiment, this isn't true at all. The maxima get less and less bright the farther you go out on your screen, or the bigger the angle here gets. And this is because every slit of the double slit has such an intensity curve which presses down here these maxima of higher order. So whenever you do this experiment, you have a bright maximum of 0th order, then some bright maxima lying near that, and then as your angle gets bigger, the intensity decreases rapidly. This is because of the single slit influence. And then under some, so here in red you see the real intensity curve of a real double slit, where I take into consideration that both slits have finite width. And sometimes it can happen that there should be a maximum, but there isn't. It gets wiped out. And this is what is explained here. Because if we have this relation that the width B of one of those slits is G, the distance of the slits here, divided by a natural number L, then it can be shown that every Lth maximum, for example, if I have B is G over 2, then every maximum of even order, 2, 4, 6, and so on, gets cancelled out because the single slit has a minimum there. And of course, if the single slit doesn't send intensity at all, there can be no maximum of the double slit. This is this calculation here. I'm asking myself, for which indices n it is true that phi sub k, meaning the angle of the minimum of order k of the single slit, equals alpha n being here the angle of the nth maximum of the double slit. And when those two coincide, as explained before, there is darkness, because here each slit doesn't send out intensity. So I apply the sine function on both sides, then I end up with, using this formula, k times lambda over b equals n times lambda over g. This comes from here. And then I solve for n, lambda cancels, and I observe that g over b, that's my assumption here, is a natural number L. So for every n of the form L times k, so L, 2L, 3L, and so on, this respective maximum vanishes because of the single slit influence. And that's about all there is to say about the double slit. Of course, you have to do some examples and do the actual calculations by yourself to really understand it, but this is, I think, the whole theory that is needed for the single and the double slit in high school. So our next diffraction object is a multiple slit, meaning not a double slit, but for example a 3 times slit, triple slit, or quadruple slit, or whatever. So I simply add a finite number of slits, and of course they must all have the same distance, because otherwise the formulas get too complicated. And then it's pretty easy, because neighboring slits then have always the same optical path difference. It's that picture here all over again. So the formula for a maximum stays exactly the same as for the double slit, because if these two wave rays here have a path difference g times sine alpha, which is a multiple of lambda, a natural multiple or 0, then of course these two, because of the same difference, have the same path difference. So if the electric field vectors of these two meet like that, then the electric field vector of this first ray is also like that, and they all add up, giving me a maximum, which means a bright spot on my screen. And now here's something new happens. So these higher peaks we already understand. The formula is exactly the same as for the double slit, but now between they are called main maxima now. I hope that's the right expression, I wasn't entirely sure. Main maxima and side maxima, hopefully. Between two main maxima there are several minima and side maxima. You can read off from this intensity curve what kind of slit you have, because between two main maxima in a multiple slit with n slits, there are always n minus 2 side maxima. Here, for example, I have n equals 4. So there are 4 slits and n minus 1 minima. Here 1, 2, 3, meaning this is a multiple slit with n equals 4. So here now there are several minima of order 1. All these are minima of order 1, but there are 3. And now I want to explain you how to find them, but first be aware these angles can be calculated directly. Here these side maxima are much more difficult. It's much more difficult to find a closed formula for them, so do not concern yourself with that, but you can memorize that the intensity of those is much smaller than the intensity of the main maxima. It goes with 1 over n squared. So there are very bright main maxima, and in between there are much less bright side maxima. So to understand what happens here, we use arrows, meaning we describe the electrical field vector of the electromagnetic light wave by taking an arrow that is rotating counterclockwise, and the y-coordinate of this arrow gives us the actual length of this electric field vector and the direction. For those who know complex numbers, these are nothing but complex numbers, and they are much easier to work with than real sine functions. This is what is mathematically behind this idea, because physically it seems strange at first glance. Why would we use a rotating arrow? And this you see depicted here when the electromagnetic wave moves to the right. Then here, of course, our arrow is like that. The y-coordinate is the length of the arrow itself, so the electrical field has a maximum. Here, the electrical field vector is 0 at this moment in time, at this point on the x-axis. So now is the question, this arrow or this arrow? Because both have y component 0, but the wave is traveling to the right, so in the next nanosecond, the electrical field will grow. And remember, our arrows rotate counterclockwise, so this arrow in the next moment goes up, giving you a positive y-coordinate, whereas an arrow pointing to the left would give you a negative y-coordinate, which would correspond to a wave moving in this direction. Now here, this is clear again, arrow must point like that, and here, as explained, it must point here, because in the next moment the electrical field vector points downwards, so the arrow must go down. And now there's a very easy to remember rule of thumb on how to find these angles where the minima of order 1 occur. The important number is the phase difference of here two neighboring arrows, delta phi 1, because minimum of order 1. You take 2 pi divided by your number of slits, here depicted for the case n equals 4. So you end up with pi over 2 or 90 degrees. So you take the arrow corresponding to the electromagnetic wave of slit 1, which points, for example, in this direction. Then the next arrow of the next slit points here, counterclockwise, 90 degrees. Then the arrow of slit 3, again, counterclockwise, 90 degrees. And now I have only two hands. The last arrow here, again, pi over 2, counterclockwise, and you end up at the point where you started. So the sum of these arrows is 0, meaning that the resulting electrical field under this angle is 0. So you have a dark spot on your screen, meaning you have found your first minimum. And then all the other angles are found by multiplication by natural numbers. So the next possibility would be pi over 2 times 2, meaning pi. First arrow like so, second arrow 180 degrees counterclockwise, third arrow like that, and fourth arrow again 180 degrees. Each two pairs cancel out, so we have our second minimum, and so on. You should do this for n equals 3, n equals 4, and maybe n equals 5. Do these little pictures and think these cases through. That's very rewarding. And then usually you're not asked at which angle is the minimum, but where on the screen is the minimum. And then there's this formula which translates the phase difference of the arrows into an actual path difference. And this you can use to calculate where on the screen, using this formula, where on the screen the minimum is. This is very easy to understand because in one wavelength, the arrow rotates 360 degrees or 2 pi radian. So the actual path difference divided by one wavelength is the same as here, the phase difference of the arrows divided by 2 pi, because again 2 pi corresponds to one wavelength. And then you can calculate your delta, the optical path difference, and using the ever same formula in Fraunhofer approximation, g times sine of the angle, you get this here. When you plug in delta phi 1, the 2 pi cancels, and you end up with lambda over n, the number of your slits. So for example, if I want to calculate the angle beta 1, 1, the first minimum of order 1, I have to find an angle such that g times sine beta is lambda over 4 in that case. And then I can find where on the screen the minimum lies. So this was also very condensed. If you speak German, please watch my other video where I explain this in depth. If you've seen it for the first time, please sit down and do these little drawings here to understand what's happening. Now the last diffraction object we're looking at is the so-called diffraction grating. This is simply a multiple slit, but the number of slits is very, very large. For example, there are gratings with 1,000 slits per millimeter. Accordingly, the G here, the distance between neighboring slits, is very, very small. And this has many advantages for experiments because the interference diffraction pattern consists simply of points, and between the points is darkness. So it's very easy to read off the right angles or the right distances, opposed to a double slit, for example, where the whole pattern is very blurry. So as I said, there are some, here in the intensity curve, there are some peaks corresponding to spots of light on your screen, and in between there's complete darkness. Theoretically, there would be a lot of side maxima and minima, but they are so small. Remember, they go with 1 over n squared in the intensity. So if I have very, very many slits, this here is almost 0, so our eye can't detect it. So in between the main maxima, there is darkness. Very important, it's very, very wrong to try to apply this formula for a minimum. Sometimes my students do that. This here is wrong. The formula for the maximum is exactly the same because we have exactly the same picture as here, only with very, very, very many slits. But here the G is always constant, so neighboring wave rays always have the same optical path difference given by this formula in Fraunhofer approximation. And then if this here, the path difference, equals n times lambda and a natural number or 0, I get the angle of a maximum where there is a bright spot. And they are very sharp because here the first minimum is very, very close to the maximum, because the angle, as you see here, or here the path difference is lambda over n, and as n grows, this here gets very, very small, which means the first minimum goes very, very close to this maximum, so these peaks are very sharp. I hope this is the right English word. Now if you take white light with a coherence slit so that you get a coherent light source, then if you here solve this formula for the angle of the nth maximum, you see, oh well, this of course depends on the wavelength, which means that red, for example, oh, here's still German. Red, for example, has a larger wavelength than, what's the American word, violet, purple, I'm not sure. This here is about 800 nanometers, and this here is about 400 nanometers. And then because the arc sine is a strictly monotonously increasing function, this whole thing for red is bigger than here the angle for the nth maximum of violet light. And then all the colors split up and you see beautiful rainbow colors, and the whole thing together gives you a spectrum of light. So all the different colors get visible when you shoot them at a diffraction grating. Again, this is very, very compact and dense, but there's no more time here to go into more detail. And those spectra can overlap if this condition here is fulfilled. Again, no more details. And to conclude, when there is matter of any kind, light travels through matter, for example glass, like in my glasses here, or water, then refraction occurs. Meaning that here a wave ray gets bent. So if this angle here is alpha and this angle here is beta, then to determine what the correspondence between these two angles is, you need Snell's law, or Snellius Law of Refraction. Here those two numbers are the refractive indices of the medium. They are defined by n of, oh, in German again. They are defined by taking the vacuum light speed, the light speed in vacuum, C0, divided by the light speed in the medium, which has to be measured. For the stuff we work with, this is always a number larger than 1. Or for air, it is about 1.000, I don't know. So we can assume that in air, the light speed of light is almost the same as in vacuum. And then the wavelength of the electromagnetic wave in this medium here is, that's a very important formula, speed of light divided by frequency. And now the frequency doesn't change because on an atomic level, the electromagnetic field induces another electromagnetic field by wiggling the electrons of the molecules or atoms in this matter, and the frequency stays the same. So the frequency is the same in vacuum or air and in water, for example. So F stays the same. Now you plug in this here and you end up with C0 divided by F, which is nothing but the wavelength in vacuum of the light wave divided by n. So because n is larger than 1, whenever light enters a medium, the wavelength gets smaller, lambda naught divided by n. And then if you have the refraction indices, Snell's law reads as follows: n1 times the sine of this angle here equals n2, the refractive index of this medium, times the sine of beta, the refractive angle. This is sometimes important if the space between the diffraction object in our screen, for example, is filled with water or glass or whatever. Okay, that's it. That concludes the summary of wave optics as needed in high school. If you're an English-speaking viewer and enjoyed this video or found it helpful, I would appreciate it very much if you would leave a comment, because usually I make these videos for my high school kids in Germany, for them to prepare for their exam. But if you find this helpful, maybe I'll think about doing some of my future videos in English. Thank you very much for watching, and maybe I'll see you later.